Hello, everybody. It's me again, Rich Andre, and today we're going to be talking about abstract algebra. Okay, and we're going to be diving into a topic, multiple topics actually, about equivalence relations, classes. Equivalence relations, equivalence classes, fibers of a function, and integers modulo n. So these basically just encompass sets, okay, and elements of sets and their relationships to each other. So let's first start explaining the different types of equivalence relations. Okay, so the first is what we call reflexive. This is going to be dumbed down as much as possible. And let's say, suppose we're talking about people. Okay, so we have Alice and Bob. Let's say Alice and Bob. We have two people. Okay, so Alice is tall. Let's say Alice is tall and Bob is short in height. Okay, so reflexive basically just says that if Alice is tall, then the relationship, okay, with Alice, the relationship of both of them is that they're tall. Is Alice is tall. Okay, so if Alice is tall, then Alice is tall. That's basically it. Okay, reflexive. Okay, so it basically just goes back to the subject. Okay, and I'm just using people in here, but we're actually using numbers later on. So the same goes with Bob. If Bob is short, then Bob is short. If Bob is short, then Bob is short. That's basically it. Okay. So that is reflexive. The first type of equivalence relations. Okay, we're going to use numbers later on, so don't worry about that. So the second type is symmetric. Okay. So what symmetric basically means, okay, we can look at example here. ChatGPT goes both ways. Okay, so if Bob, okay, let's say if Bob is a sibling of Alice, then Alice is a sibling of Bob. That is what a symmetric equivalence relation is. Okay, so the third one would be transitive. Okay, so let's say we have three people: Alice, Bob, and Mary. So if Alice, okay, let's say we have this hypothetical argument. If Alice has the same birthday as Bob, and Bob has the same birthday as Alice as well, okay? If Alice has the same birthday as Bob, and Bob has the same birthday as Alice, as Mary, sorry, same birthday as Mary, then we could safely say that Alice has the same birthday as Mary. Okay, so that is what a transitive is. Okay, there is a relationship. Okay, with the first variable to the second variable, The second variable has a relationship to the third variable, then the first variable has a relationship to the third variable. That's a transitive equivalence relation. Okay. So what is a class? Okay. What is an equivalence class? This is just my understanding only. Okay. So let's say we have this. We have a bracket, and enclosed in the bracket is a letter A. Let's say we have a set. Let's say we have a set of positive integers. Okay. So let's say 1, 2, 3, 4. Yeah. Say 1, 2, 3, 4. A class is basically just a sort of group, a group of a set, sort of like a group of an element in elements in a certain set. So in element Z, let's say we have 1 and 2 for the class A. That's going to be what classes are. Basically, just groups of how many many numbers. Okay, how many ever numbers that in or elements in a certain set. That's basically what a class is. Okay. So about fibers. Okay. Fibers of a function. The best way I can explain it is through an analogy. Okay. Let's say we have Alice, Bob, Mary, and Joseph. Excuse my bad handwriting. Let's say they're in school. Okay. Let's say that these people are in school. They're in different classes. They're in different classrooms. So let's say Alice is in class 101. Bob is in 102. Mary is in 101, and Joseph is in 102. Now, who has the same classes? Well, first, okay, is Alice. Mary, and Bob, Joseph. Okay. That's basically it for fibers of a function. That's an oversimplified version of it, but I think that sufficiently explains how a fibers work and function. Let's say you have apples. So let's put another example, just in case you didn't know or didn't understand what it is that I'm trying to say. Okay, so let's say you have fruits. Okay, let's say you have apples, you have mangoes, you have peaches. Okay, so let's say you have a basket. Let's say you have basket 1, basket 2, basket 3. Let's say you have 2 baskets, and say you have two. Oh, that's a bad example. Let me just. I'll just get rid of that. I think the first example is sufficient enough to explain what a fibers of a function is. So we can just leave it at that. Okay. So integers modulo n. Let's say you're trying to divide 10 and 4. Okay. Let's divide it by 3. So if we divide it by 3, okay, how many 3's are in 10? 3. How many 3's are in 3? Are in 4? 1, okay? So the integer modulo n is basically just saying, okay, how much the remainder is. So how much is the remainder in 10 divided by 3? It's 1. And it's 1 as well. 4 divided by 3 is 3. There's a remainder of 1. So that's basically what integers modulo n means in abstract algebra. Okay, so let's try to solve a few questions. Here in Claude, I actually searched a few. I actually prepared a little bit of a test here. So let's try to test our knowledge in the topic. Okay, so we have which property does this relation fail to satisfy? Okay. By the way, okay, the symbols. Okay, the tilde. Okay, this little symbol right here basically just means relates to. So if we have A tilde B, basically just means that A has a relation to B in some significant way. Okay, so let's try to go back. Okay, let's try to go back here. Let's try to go back to the problem. Which property does this relation fail to satisfy? On Z, define A is related to B if A is greater than B. Okay. Okay, so if A is greater than B, okay. If A is A is less than B, if A is less than B, okay, then B is greater than A. Okay? If A is less than B, B is greater than A. If A is less than B, then A is less than B. If B is greater than A, then B is greater than A. So reflexive is correct. It satisfies the reflexive property. How about a symmetric? Okay. If A is related to B and A is less than B, could A be greater than A? Could A be greater than B? If B is greater than A, could A be greater than B? No. It's not possible, so it's not symmetric. How about transitive? Transitive, you need three variables. So if I'm going to reduce this, okay, I'm just going to make a sort of like a educated guess on what the answer is. I'm just going to answer A. Correct. Okay. So I'm correct. It says correct if else reflexive and symmetric. Reflexive, A is less than A. It's never true. Nothing is less than itself. Okay. For symmetric, if A is less than B, A2 is less than 5, it does not follow that B is less than A. Okay. Equivalence plus all three parts, so it's not one. Okay, so it is correct. It's correct. On a set of, let's go to problem 2. On a set of people, define A is related to relation to B. If prime A, okay, and B were born in the same year. No, that was not prime. Okay. On a set of people, define A's relation to B if A and B were born in the same year. Which property does not satisfy? So let's try to write that down. Okay. Let's try to write that down. A is related to B if A and B were born in the same year. So they're only related if and only if A and B were born in the same year. So let's try to make examples out of that. Okay. Let's say we have Alice and Bob again. Okay. Let's try with the reflexive property. Alice was born the same year. As Alice. Bob was born in the same year as Bob. So reflexive is correct. Reflexive property is correct. Okay, it satisfies the reflexive property. How about the symmetric? Okay, so if Alice has the same year as, let's say Alice born in the same year. Okay, so this is actually wrong. I think it's wrong because the relation is only when A and B were born in the same year, so it's obviously going to be symmetric. But apparently there's okay, so let's go back again. Let's try to reread the problem. We're born in the same year. It can be reflexive and symmetric. Because if Alice was born in the same year as Bob, then Bob was born in the same year as Alice, then Alice would be born in the same year with Bob, and then Bob would be born in the same year as Alice. So that's very good reflection. So apparently we're wrong. It says here all three hold. Reflexive were born in the same year, so when I share something, when I share the order doesn't matter. And Alice and Bob share a birthday. Bob share a birthday. Bob and Carol share a birthday. Then Alice and Carol also share a birthday. So this is a genuine equivalence relation. The only thing that I got confused in this problem is because Carol, okay, the other variable, the last variable is not mentioned. If it was mentioned, then obviously I'm going to be able to answer that all three hold. But I sort of had the intuition that all three of these relations hold. Okay? So that was a good try nonetheless. So let's try this problem tree. Define A is related to B on C if A and B have the same parity, both even or odd, both odd. What is the equivalence class tree? Okay. So it says here, what is the equivalence class? We're going back to equivalence class, okay? Equivalence class is basically just a group in a certain Z, in a certain set. So if we try to decipher the questions here, we're trying to decipher the question here. So let's say, it says here that A is related to B on Z on the set if A and B have the same parity. So when it says parity, okay, so let's say odd and even. Okay. Can be both odd and both even. Let's say you have a Z, okay? Z is positive integers. Equivalence class C. We're trying to find equivalence class C. So let's say the equivalence class of 3. So we're talking about pairs here. 3 and 4. If we take this as a first pair, and we take this as the second pair, we're trying to find, okay, the relationship. If both of them are both odd and even, then only then will A and B be related to each other. And we're trying to find, okay, 3. Trying to find 3. Okay. So 3 and 4. Are they both odd and even? both even or both odd. No, they're not both odd or even. This is odd, and this is even. So if they're different, then they have no sort of relation whatsoever. So what is the equivalence class? 3. Just 3. Okay, so Claude has some sort of advice here. So it says here, if the tree is a set of everything equivalent to 3, meaning everything at the same parity is 3. Since 3 is odd, all odd integers, note that 3 is equal to 3 is equal to 1 and negative 7. I see. So if 3 is odd, we're going to find the same category as 3. So 3 is just a representative of the odd numbers that are included in all the integers. Okay. So I guess that would be it for this video. I'm not going to go through all the questions, but that was a good attempt, And I think I learned a lot in this lesson. Hopefully you learned some too, So this is just abstract algebra, Sorry if I didn't get through all of the problems. Hopefully I can get through some of it privately without recording, but this will be the entire video. Abstract algebra about equivalence relations, equivalence classes, five-cell function, integers, modulo n. Thank you guys for watching. I'll see you guys in another video. Peace.